Thank you organizers for this presentation opportunity and welcome to my talk. Today I will take you on a correlative microscopy journey highlighting large 3D EBSD using laser plasma FIB-SEM. I will brief on correlative microscopy and serial sectioning methods for 3D EBSD. Next, I will prove laser ablated surfaces are suitable for EBSD. Subsequently, I will describe tri-beam system for large volume 3D EBSD data collection. This will be followed with examples and summary. Now let's meet scientists Alice and Bob. Alice and her group is focusing on natural materials, while Bob and his group is dealing with man-made materials. They are facing challenges in multi-scale characterization of materials, in particular microstructure characterization. They are meeting Gary to get an insight into multi-scale and multimodal characterization techniques. Here we see the landscape of machining, characterization, and testing techniques in 2D and 3D, applied at various length scales. These likely solve 99% of research problems at all length scales, but let's focus on SEM-based serial sectioning techniques. There are several automated techniques for 3D EBSD data collection that span from macro to submicron scale: mechanical polishing, broad ion beam milling, plasma FIB, gallium FIB, and now laser PFIB that really bridges the gap between large macro scale volumes and micron scale datasets. These have much higher material removal rates, thus much larger material volumes are accessed. Simultaneously, the damage induced by material removal is in dozens of nanometer range, similar to FIB or mechanical polishing. Now the key material factors for EBSD data collection: obviously crystalline solids, pristine surface finish, roughness in nanometer range, and intact crystal structure during material removal. One can account for continuous, chopped, and pulsed laser emitting electromagnetic field at a specific wavelength and having a few other parameters. Here are the main parameters that are used hereafter. The fluence have a spatial distribution close to a Gaussian profile, and the beam is shaped and focused on a certain point in space, typically at the ablated surfaces. There are plenty of commercial lasers having different power parameters and wavelengths. The most common is carbide, ultra-short pulsed laser tuned to green and near-infrared pulses, fast and precise material removal, and ultra-fast material removal. Simplifying largely, laser electromagnetic radiation interact only with electrons of material atoms, since nuclei are too heavy. The processes vary for metals, semiconductors, and dielectrics. Here is the timeline of electron and lattice processes in laser irradiated solids. Femtosecond laser pulses transfer energy during carrier excitation and thermalization. Subsequent processes follow without external energy. While being close to ablation threshold, the other thermal and structural effects are suppressed to a negligible level. Very high fluences transfer so much energy, causing pronounced thermal and structural effects. Picosecond laser pulses transfer energy much longer, energizing thermal and structural effects. The stronger effects, the higher fluences is used. The same general rule applies to nanosecond laser pulses. Here is the comparison graphics of ultra-short pulse laser and long pulse laser. By shortening the pulse duration, we can suppress all thermal and other resulting effects, therefore allowing athermal material removal. During laser ablation, we are glancing the surface with the laser beam, therefore we are using the low fluence area of the beam during the laser scanning. We can approach the surface and scan to remove the layer. In this glancing scanning action, laser typically generates nano-sized periodic structure with characteristics depending on the various factors. For example, the polarization. Does this fit the bill for proper EBSD data collection? Let's have a closer look. Let's look at the copper polycrystal. Yes, we can collect EBSD maps, but the ellipse pattern distorts the view. TM data clearly shows increased density of dislocations and lattice distortion. Overall, we have a quite good results that can be noise reduced later. Now if we look closer at the sample surface and electron's incident angle, we can see the influence of the surface topography on the formation of Kikuchi pattern on the EBSD detector. Here's a clean signal configuration and a shadowed pattern. These produce misindexed periodic locations. Hard metal composite also has lip structure, but without severe lattice damage or amorphization. Laser action at glancing angles is quite material agnostic, as indicated by the line profile. However, the lip structure rather severely obscured the EBSD maps, while producing quality EBSPs for the material constituents. How can we remove the lips? We can use plasma FIB to gently polish the surface at near glancing angles. Here we see polished surface and EBSD maps. There is a clear improvement in indexing rates, and here is comparison with the laser-treated surface. Some tungsten carbide grains have lower index rates after PFIB treatment. It is a known feature for these materials. Other results from the literature indicate similarities, for example, gallium nitride, while others have greater improvement after FIB action. However, if you are stubborn enough, you can fine-tune the laser parameters to vanish the periodic structures. Here are examples on a copper. Our latest ultramicroscopy paper on exploration of the laser ablation parameter space for 2D and 3D imaging of soft and hard materials by tri-beam microscopy serves a good starting point for those interested in examining large area or volumes across a range of materials using tri-beam microscopy. The graph illustrates a parameter space for average power across various materials, indicating the minimal occurrence of lip structure. Additionally, it incorporates results from other researchers. The laser and optics are fully integrated with the latest Helios Hydra FIB-SEM platform, thus xenon, argon, oxygen and nitrogen primary ions beam are available. 3 beams are positioned on a plane and coincide in a point. The system can be equipped with analytical detectors. It has monochromated L-star SEM column, high resolution PFIB column with sharp and rapid milling high currents, various electron and ion detectors, and a dual wavelength femtosecond laser. It is equipped with automated column protective shutters, piezo stage, all controlled by API Python programming interface. Here is the laser ablation configuration and several control parameters in the UI. These are automated shutters. Here is PFIB cleaning configuration. SEM EDS imaging configuration. And EBSD EDS mapping configuration. Here is a summary of experimental times for a typical millimeter range 3D BSD volume. Worth pointing here is that the bottleneck is still EBSD mapping. 3D workflows are controlled or customized in Laser UI or via Python scripting. These control acquisition hardware and software. Various data sets are sequentially collected. These are assembled in 3D and processed with a VISO package or other packages. Here are the latest correlative microscopy results for stress corrosion cracking in aluminum alloys. X-ray survey scan, X-ray high resolution scan, and finally large volume 3D BSD in the region selected from the CT data. Next one is laser additively printed of cobalt superalloy collected by scientists from Santa Barbara. There are plenty other large volume 3D BSD examples and serial section of various materials systems, including electronics and soft biomaterials. Laser Hydra PFIB is also a central instrument for correlative microscopy workflow. With this instrument, one can machine specimens for micro X-ray CT, lamellas for TM study, or APT samples and use it as a 3D data collection instrument. The correlative microscopy is aided with cross-platform holder kit and coordinate locking mechanism. Here's an example of correlative study of sparsely distributed defects in glass fiber composite that uses this workflow. The in situ laser PFIB has wide range of applications not accessible by ex situ laser configurations, for example 3D EBSD DS mapping, laser beam assisted chemistry, laser processing at cryogenic conditions, etc. Femtosecond laser allows rapid machining of damage-free serial sections over mm² areas. In the most of the cases, EBSD data are collected directly after laser ablation. If needed, LIPS roughness is removed by FIB cleaning or fine-tuning of laser parameters. The laser unit is fully integrated in the Helios PFIB platform. 3D EBSD data collection automation is compatible with third-party vendors. Laser FIB-SEM is compatible with cryogenic stages. The instrument is the central part of the correlative microscopy workflows. After all, it's a fully functioning Hydra Plasma FIB-SEM platform. I also encourage you to familiarize yourself with our latest ultramicroscopy paper, which explores the laser ablation parameter space for 2D and 3D imaging of soft and hard materials by tri-beam microscopy. Thank you for your attention.